begin our discussion on enzyme kinetics in this module that follows enzymes and enzyme mechanisms. In this particular model, we will be looking at the Michaelis-Menten equation, Briggs-Haldane assumption, the Lineweaver-Burke plot, and what the significance of these kinetic parameters are, and what we mean by the turnover number of an enzyme. These concepts are important in understanding the saturation kinetics and the specificity of specific substrates, specific enzymes, and how we can design specific inhibitors and how we can compare over inhibitors. If we look at the concept of enzyme kinetics, what we are looking at is we are looking at a velocity as the reaction, the enzyme substrate reaction proceeds, where we have the formation of the enzyme substrate complex in the event that it will form the product, as we have seen in the previous module, the velocity of this reaction decreases if there is a decrease in substrate concentration, product inhibition occurs, and there are pH changes and thermal inactivation of the enzyme itself, as we saw that the enzymes work at an optimum temperature and at an optimum pH. So if we look at the formation of the product with time, or we follow the rate of the product with time, then what we can look at is the formation of the product, and this slope gives us our initial velocity. So over time, we see that we reach a saturation as the product is formed, indicating that their substrate has been converted into product. As we look at a reaction of the initial velocity now versus the substrate concentration, what we see that in a catalyzed reaction, we can reach this saturation much earlier than before. So the initial velocity of this enzymatic reaction diminishes with substrate concentration, giving us saturation kinetics, indicating that with time, the enzyme is saturated with the substrate and further reaction is not possible. Initial velocities of these enzyme catalyzed reactions can vary with the substrate concentration, in the sense that the more of the substrate we have, the product concentration, as would be expected, would increase. But for each of these initial values, we will get a velocity associated with the substrate. So we will have a velocity, an initial velocity, as corresponding to each substrate concentration. This is important in understanding how we can define our system. So the substrate concentration will affect the rate of this enzyme catalyzed reaction. The formation of this enzyme substrate complex occurs in a relatively fast reversible step. So this is our first reaction that occurs, where we have our substrate forming a complex with the enzyme in this enzyme substrate complex. The enzyme substrate complex has a forward rate constant of K1 and an inverse rate constant of K minus 1. This is similar to the protein ligand binding studies that we considered in a previous module, where we looked at the ligand binding to the protein in a forward rate constant and a reverse rate constant, which would amount to the dissociation, in this case, of the enzyme substrate complex to form the enzyme and the substrate again. This breakdown of the ES complex now will result in a product formation in a simple representation, where we look at the enzyme substrate complex break down to form the enzyme and the product. So this enzyme now is ready to form or to accept another substrate. In this specific set, we are looking at another equilibrium, but considering that the product formation occurs at a rate where we follow the formation of the product, it at times is considered unlikely for this to revert back to the enzyme substrate complex in a reversible reaction in this case. So assuming that this reverse reaction P2S is very slow, we can say that the rate constant associated with K minus 2, that is the reverse of the second reaction or the second step, is very slow. As a result, the overall reaction can now be written in a fashion where we have what is called a pre-equilibrium step associated with the enzyme substrate complex and its possible dissociation, and a second step that involves a rate constant K2 in the dissociation of the enzyme substrate complex to form the enzyme and the product. The initial enzyme now, the rate constant of the formation of the product, therefore, is our K2 rate constant and the concentration of the enzyme substrate complex. The total enzyme concentration, as we know, is ET. So, like our ligand concentration, we would know the amount of the free enzyme in solution, similarly to our protein ligand binding kinetics. Here, the enzyme is either in the free form or in the bound form. In this bound form, it is in the complex of the enzyme substrate. So we have the total enzyme concentration minus the enzyme substrate concentration would give us the free or the unbound enzyme, and from this we can study different kinetics of the enzyme. The step 1 therefore looks at the rate of the enzyme substrate formation. The enzyme substrate formation is followed by K1, that is the first reaction that we have, where we have E plus S in our first step in the specific rate constants K minus 1 forming our ES complex. This then dissociating into E plus P in our second step. So this is the rate of ES formation, and we have the rate of ES breakdown given by the dissociation in the reverse direction, the K minus 1 that we have here, and in the forward direction to the formation of the product. In step 2, we use what is called a steady state assumption. In the steady state assumption, we assume that the concentration of ES with time does not change. So DES dt is equal to 0. So we can equate the rate of ES formation to the rate of ES breakdown, and this leads us to a formation that we can consider in a graphical representation like this, where we have our enzyme concentration and our substrate concentration, both of which decrease with time. Our time is on the x-axis and the concentrations of the different species in solution is given as these different lines. So we have our enzyme concentration and our substrate concentration both decreasing with time, and our enzyme substrate concentration initially rising and then being constant, while our product is rising and then reaches a saturation with the depletion of the substrate. This is the Briggs-Haldane assumption, where ES, that is our enzyme substrate complex, is at a steady state saying that there is no change in the concentration with time, as the corresponding constant is Km, that is the Michaelis constant defined by K minus 1 plus K2 divided by K1. Step 3 involves solving this equation for ES. So we have the equality related to the formation of ES and the disintegration of ES, which we have equated. From that, with a bit of algebra where we take the concentration of the substrates and the enzyme substrate complexes to one side, and we have the enzyme substrate complex concentration that we have excluded from the brackets here. And what we have is we have an expression for the enzyme substrate concentration. From this, we can work out a bit of algebra divided by K1 throughout this equation, giving us this specific constant. This we work out to be the Michaelis-Menten constant. This Michaelis constant is given by, therefore, this expression, which we will look at in more detail to understand about the expressions. So if we rewrite equation 4, which is this, where we had our V0, that is the initial velocity, given as the K2, that is the second step, and the product of the ES complex, we can get an expression that is equal to this. This helps us in an understanding of the enzyme substrate formation. Now, we can work out specific options or specific possibilities. If we say that the enzyme substrate complex concentration is equal to the total enzyme concentration, this means that the enzyme is saturated, which means that we have reached the maximum velocity possible, that is K2 into the total enzyme concentration, considering that the reaction is to completion. So we can write out K2 ET as Vmax S from our previous expression. So we have an initial velocity, we have the maximum velocity, and we have this in terms of the substrate concentration. This is the Michaelis-Menten equation, and the rate equation is for a one substrate enzyme catalyzed reaction. Now, the resulting Michaelis-Menten equation that is shown here can now be looked for, where we have now the V0 versus the substrate concentration. We will reach the maximum velocity, and at half the Vmax, the substrate concentration corresponding to half Vmax, we will see if we can plug these values in here, where we make V0 equal to Vmax by 2, that is half of Vmax. We will get Km equal to corresponding to that substrate concentration. So the Michaelis-Menten constant gives us a constant that is useful in comparing substrates, and the saturation kinetics of enzymes is described by these two measurable parameters, that is the Vmax of the reaction and the Km of the reaction. This is what describes our enzyme kinetics. So it is the substrate concentration that yields half of the Vmax, and Vmax is the maximal velocity at high substrate concentrations. So let us look at various possibilities. So here is our equation, our specific expression for the enzyme substrate complex formation and its subsequent formation of the products. Now, the assumptions of this Michaelis-Menten model say that the The enzyme is at a fixed concentration and the reaction involves two basic steps. One is a fast equilibrium process where we can have the fast formation, where we have now an equilibrium which we define as the backward reaction rate divided by the forward reaction rate, where we have our K inverse process much larger than the K2. We can have the catalysis and substrate release that is slow, where we have a K2 less than a K1, and rate limiting, where we have what is called a K-cat that is associated with the K2, where we will have our initial velocity correspond to the second step of our reaction multiplied by the product of the enzyme substrate concentration. If we look now at the interpretation of the saturation kinetics in terms of the curve where we plot the initial velocity versus the substrate concentration, initially we considered a first order reaction followed by a second order reaction. So this is our expression. And if we look at the substrate concentration that is much greater than the Michaelis constant, then we can form our equation in such a way that if we just plug this possibility into this equation, what we say that the Km plus the substrate concentration is very close to the total substrate concentration, as a result of which we can get the V0 equal to the Vmax when the substrate concentration is very high. So when we reach this Vmax possibility, we say that we have our Kcat into the product of the ES substrate, ES complex, and Kcat is approximately equal to K2 when the enzyme substrate complex corresponds to the total enzyme concentration available. So we have our V0 equal to KT, K2 ET instead of ES. Another possibility that we can look at is when the substrate concentration is close to the equal to the Km, which is the way we defined our Km value. That is, the V0 would be equal to Vmax by 2 at Km. So the Km definition is the substrate concentration when the velocity has reached half maximal velocity. Another possibility would be where we have the substrate concentration much less than the Km value. In this case, our Km plus the substrate concentration is approximately equal to the Km, and we rearrange this equation where we neglect the concentration of S in the denominator and we get an expression for V0. Now, if this means that then the enzyme concentration is equal to the final concentration, and we can say that Kcat by Km in an expression for the substrate concentration, giving us a pseudo second order rate constant where EF is a constant, considering that the substrate concentration is less than the Km value. Our next expression looks at a linearization of our Michaelis-Menten. This is by far the most useful plot in enzyme kinetics, where we can actually determine the value of Vmax and Km from a reciprocal, a double reciprocal plot as it is called, where we get the form of y is equal to mx plus c, where we realize that if we plot 1 by V0 versus 1 by substrate concentration, our slope is going to correspond to Km by Vmax. So this is what we plot in our double reciprocal plot, 1 by V0 versus 1 by S. This linearization gives us a value for 1 by Vmax and the negative intercept on the x-axis as minus 1 by Km, and this intersection, the intercept on the y-axis, giving us 1 by Vmax. We realize that this is a much easier representation in the sense when we plot the V0 versus the substrate concentration, and we get a plot that is in this fashion, identifying or trying to determine the Vmax, or the half of the Vmax that is going to correspond to the Km value, is not an easy task. However, when we have this double reciprocal plot, that makes the job much easier. So in our double reciprocal plot, we found out that if we plot 1 by V0 versus 1 by S, we can get the slope and the intercepts that will give us the values of Km and Vmax. So this is our expression, and this linear representation can work with even 5 values of the substrate concentration, and we can determine Km and Vmax, which is what we can use to compare over different substrates, comparing the Km constants, comparing the maximal velocities. Now the significance of these kinetic parameters. We have the Km equal to the K minus 1 plus K2 by K1. Neglecting the value of K2, considering that it is really small, we can get an inverse measure of the affinity of the enzyme substrate complex. So this is like the association and dissociation constants that we considered for protein ligand binding. Now, for the enzyme substrate concentration or the enzyme substrate complex formation, we do not want this to be too strong, because if the enzyme substrate complex is a very tight complex, then the substrate or the reaction would not proceed and we would not have product formation. Another possibility is the Vmax that corresponds to the maximum velocity, where we have the kcat value that gives us the Vmax divided by the enzyme concentration. This gives us a measure of the reaction efficiency. So we have the affinity, we have the efficiency. And a perfect enzyme would have a kcat value of the order 10 to the 7 second inverse, and an average enzyme, a rule of thumb, would be 10 second inverse. So we have a specificity constant that we can define that would give us Vmax by ET, that tells us the specificity, and we have the specific variations that we looked at that tell us what a perfect enzyme would be in terms of its specificity. So we would want our catalytic protein, that is an enzyme, to be specific in nature, to be efficient, and to have a perfect kinetics in the sense of product formation. We define therefore now the turnover number. This is the number of substrate molecules that are converted to product in a given unit of time on a single enzyme molecule when the enzyme is saturated with the substrate. Now, in the Michaelis-Menten equation, we look at that as kcat by Vmax by ET, and we can work this out in terms of our expression, and the unit of kcat is second inverse. So it tells us how the turnover of the substrate molecule to the product is. It is a first order rate constant. Similarly, we can have deviations from the kinetics as well, and these deviations occur when there are multiple catalytic steps where we cannot equate the K2 with the kcat. ES, the enzyme substrate complex, is not exactly a steady state, and the enzyme displays cooperativity where we can have distinctions which we looked at in the protein ligand situation, where the binding of the substrate could have an effect on the binding of another substrate molecule, where we will be looking at double bi-substrate kinetics, where we have multiple substrates, and this substrate binding is irreversible in the sense that there is a covalent linkage that cannot be broken. So, in the Michaelis-Menten kinetics, what we look at is we look at a saturation indicating that we have our enzyme of interest that is now bound to a substrate so we have our enzyme that has taken up a substrate, and in a pre-equilibrium step that involves a forward reaction rate of K1 and reverse reaction rate of K minus 1, forming our enzyme substrate complex. And this, in a simplistic way, forms using the rate constant K2 is going to give our enzyme plus the product. In the enzyme mechanisms that we looked at, we found out that our enzyme that we started off with is now available for further substrate bound to it to have a further reaction occur to form the product. This is important, and our expression for the Michaelis constant and Michaelis-Menten kinetics indicated that we could consider a steady state assumption for the ES complex, where we equated its rate of formation with its rate of disintegration, and we got expressions for the Michaelis constant. We then found out that if we look at a double reciprocal plot where we have each of these plots at various substrate concentration, give us specific initial velocities that were the initial slopes of the graphs. If we now plot 1 by V0 versus 1 by S in our double reciprocal plot, the Lineweaver-Burk plot, we are able to get on the x-axis the value equal to minus 1 by Km, the intercept on the x-axis, and our intercept on the y-axis corresponded to the 1 by Vmax information about our proteins, about our enzyme. We also could understand what a specificity constant is, because we would like our enzyme to have a strong affinity for the substrate, but the binding should not be too tight, because we would want this further reaction to go forward to form the product. So, this is the basics of enzyme kinetics. We will look at multi-substrate reactions and see how we can describe their kinetics in the next lecture. These are the references. Thank you.